Welcome back, friends. This is our second discussion on the topic related to the Laplace transform. I am Shankar from CMR Institute of Technology, the Dean for Academics and Research. Let us take a quick recap of what we did in the last discussion. First, we looked at a function which is going in the positive non-negative real axis into that is going into the reals minus infinity infinity, and given some function like that, we were able to define the Laplace transform. We denoted it this as the Laplace transform operator symbol f of s capital corresponding to this lowercase f of s, and we defined it as this integral where s is a complex number and it has to be frequency because we are multiplying it by time here in the exponent, and that is how we defined this. Then we saw the linearity property of this Laplace transform given by this. We defined, for instance, the unit step function, which is a standard function that you have known. We derived its Laplace transform as 1 over s. Then we went through the Euler's formula. Please observe this EU is I in German. So, it is not Euler, it is Euler, because EU is a German and EU is I. Therefore, this is not Euler's formula, it is Euler's formula. So, Euler's formula is e to the power of j omega t, which is cos omega t plus j sin omega t. Through that and applying this formula using the exponentiation property also, which we had, that integral, we had this Laplace transform of e to the power of a t f of t is f of s minus a. So, using this formula we were able to arrive at the Laplace transform of cos omega t as this and Laplace transform of sin omega t as omega by s squared plus omega squared. Then we defined some very important object which is called the unit impulse, and I said it has to be defined only through an integral, and it is the shifting property. It picks that value of f of t when you take it through this integral, which means delta of t minus t naught f of t dt integrated between minus infinity and infinity will give you just one value, which is the value of f of t at t equal to t naught. If this t naught equal to 0, we get f of 0. So, that is straightforward. Now, with this definition of the unit impulse, we were able to derive the Laplace transform of the unit impulse as 1. Then we asked that we are required to apply the Laplace transformation to the differential of a function, because we took the example of an inductor, and then from there we thought we derived this formula for the Laplace transform of the differential of f of t, which is s f of s minus f of 0. Now, there are certain cautions that we must bear in mind when we get into the definition of Laplace transform itself. That is, there are some of the things which I did not mention in detail in the last lecture. I hinted it. Now, let us get into that. For instance, you have this, there is the usual confusion. I have Laplace transform of cos omega t, Laplace transform of sin omega t, and if I were to ask what is the Laplace transform of tan omega t, all right, please understand, it is not, for instance, the Laplace transform of sin omega t divided by Laplace transform of cos omega t. This is not what it is, all right. Now, there is another important thing about this Laplace transform of this particular function, which is tan omega t, and that brings us to the question of what sorts of functions f of t are Laplace transformable. All right. Now, just to make a summary statement, this is which f of t is Laplace transformable. That is the question. Now, the technically correct statement is f of t must be 1 regular and 2 of exponential order. Let me get to this. Regular, it is a technicality, I will not get into that too much, but then of exponential order, what it means is, if I have an exponentially growing function like this, k, I have e to the power of some kt, let us say k is positive, that is an exponentially growing function. Now, I am going to multiply this by another c constant, real constant c, then this function will, the function that we are looking at will be smaller than a function which is like this in the sense of the modulus. Okay? That is called the function of exponential order. So, let me just write it here. Modulus of f of t must be less than this for c k real, positive and finite. This is what it means. Okay? So, if this is true, then we say the function is of exponential order, which means, for instance, if you now, what is the use of defining something like this? If you have a function e to the power of 100t, now if I take this k to be 101, then you will definitely get this property which is satisfied. Whereas, if I take a function which is like this, e to the power of t squared, even if it is 0.00001 t squared, because of this t squared here, this function cannot be bounded like this. So, this is not of exponential order, right. That is what we mean by function of exponential order. Only such functions are Laplace transformable, all right. So, f of t is Laplace transformable if f of t is regular and it is of exponential order. Now, we took the question of tan of x, tan omega t, or let us look at tan of x against x. Now, this is 0, this is pi by 2, this is minus pi by 2. You know that the tangent function goes like this, which means in the limit as as x goes to pi by 2, from this side the tan of this is tan of x, that is x, this is tan of x goes to infinity. Now, if when you approach pi by 2 from the right, it goes to minus infinity and the function goes like this. Therefore, a function which is like this is not of exponential order. Therefore, you should not ask what is the Laplace transform of tan of omega t or tan of x. Okay? So, there are some functions which are not Laplace transformable, but then the good news for us is most of the functions that we are going to deal with, for instance, the step, the sinusoids, then there are other class of functions, other functions which are called ramp and so on. Most of these functions, or definitely all these functions, are Laplace transformable. And we have seen here on this side that the impulse, all these functions which are useful to us are Laplace transformable. Therefore, the technicality that I brought in discussing the Laplace transform of tan of omega t does not arise in our context of the circuit analysis. So, to that extent we are happy, but then it must be borne in mind if such a question were to arise. Now, I spoke of unit step, unit impulse, unit step, and I introduced a term called ramp. Now, let us understand what this function ramp is. We denote it by r of t and it is defined like this. It is t for t greater than or equal to 0, it is 0 else. Straightforward to plot this. This is t, this is r of t, this is 0. To the left of 0, it is 0. To the right of 0, it is t. At t equal to 0, t is equal, you get 0 only. Therefore, it is not a discontinuous function. This is what happens. All right. Now, which means if this is 2, this is also 2, which means it is unit ramp. If I multiply this by a constant, if you multiply this by 2, then it becomes twice ramp, that is not a unit ramp. So, unit ramp is defined like this, okay, and this in particular is continuous. whereas your unit step, let us recall, the unit step was like this, it is discontinuous at t equal to 0. This was u of t, you will recall, this is 1, this is 0, t, to the left of 0 it was 0, and at 0 it was 1, therefore, I put the dot here, and here it is this. At t equal to 0, there is a jump, this is discontinuous at t equal to 0, and the magnitude of the discontinuity is 1. All right. Now, this is another important function which we are having here. Now, what we want to do is, what is the relationship between this and this? Let us look at that. Okay. Now, I ask, what is the slope of this function? What is the slope of this function? If I were to take the slope of this function, to the left of this, its derivative is 0. That means dr of t by dt equal to 0 on this side, to the left of 0, whereas to the right of 0, dr of t by dt, for t greater than 0 it is t, therefore, if I differentiate this, I will get it as 1, this is to the, for t greater than or equal to 0, this is for t less than 0. Now, look at this, for t less than 0 this is 0, for t greater than 0 it is 1. What does it tell you? Look at the unit step. For t less than 0, this else is the same as t less than 0. So, for t less than 0, the differential of the lamp is what u of t is when t is less than 0. For t greater than or equal to 0, the differential of the ramp is the same as what it is for u of t. Therefore, what it tells us is, d by dt of r of t equal to u of t. All right. So, that is the definition that we are going, that is the relationship that we are going to get between the ramp, unit ramp and the unit step. So, let us bear that in mind. So, having defined the ramp like this, we are going to have this relationship. There are two ways in which we can get the Laplace transform of the unit ramp. All right. Now, Laplace transform of r of t, which is the same as r of s, which is Laplace transform of r of t. Let us compute this. Now, I can write the Laplace transform, I can do it in two ways, one in the time domain and one through the differential property that we had here. Now, let me do this using that property. Now, this is the Laplace transform of integral, this is 0 to infinity e to the power of minus s t. What is r of t? T is greater than 0, and for t greater than 0, r of t is t dt. Okay. Now, let us integrate this by parts. Now, let me take this as the first function, let me take this as the second function. This I take the first function, I will take this as the second function. All right. Now, this is t into integral of this e to the power of minus s t divided by minus s, this taken between 0, t going between 0 and infinity, minus integral of the second function, which is e to the power of minus s t divided by minus s, into differential of the first function, which is 1, differential of t is 1 going from 0 to infinity. All right. Now, let us look at this. Now, the right hand side, the second term is easier. So, you get plus here because you have a minus here. So, it is integral e to the minus s t 1 over s, I am taking this s outside, I get plus 1 over s e to the minus s t dt going between 0 and infinity. Now, let us evaluate this. At t equal to, as t tends to infinity, you have t e to the power of minus s t, this goes to 0. So, you have this equal to 0 minus as t goes to 0, this itself will go to 0. So, that becomes 0. Please observe, as t goes to infinity, this goes to 0, therefore, the entire object goes to 0, whereas as t infinity, whereas as t goes to 0, this goes to 0, this goes to 1, again the product goes to 0. Therefore, you have only that on the right hand side. And what is this? You have e to the power of minus st to, you have 1 over s, e to the power of minus st, that minus st divided by minus s, again going between 0 and infinity. So, for want of space, let me take that up here. So, the right hand side is r of s, the left hand side is r of s, that which is equal to, you have 1 over s squared minus 1 over s squared, and you have e to the minus st going between 0 and infinity. Now, you will see that this is as t 1 over s squared minus 1 over s squared. As t goes to infinity, this goes to 0, and as t goes to 0, this goes to 1. So, that is the same as 1 over s squared, right. So, that is straightforward. So, we have this result, r of s is 1 over s squared. Let us arrive at it in a different form. We had seen, for instance, that r of t equal to d, we had seen that d by u of t equal to d by dt of r of t, all right. Now, you also saw that Laplace transform of, I will call the differential of f of t as f dash of t, that is s times f of s minus f 0. Now, what I need to take the differential of this. Now, through this, let me try and get the differential for this, all right. That is, given this, I am going to get the differential for the Laplace transform for u of t, which is u of s. Now, in this formula, if you supply, if you say f of t equal to r of t, if I substitute f of t equal to r of t in this, what I am going to get is Laplace transform of d by dt of r of t, that should be equal to s times Laplace transform of s times r of s, Laplace transform of f of s, which is Laplace transform of r of t, which is r of s, and then what is r of 0? At 0, you saw that was minus r of 0, which is the same as s times 1 over s into 1 over s squared, that is 1 over s, and this is exactly what was our u of s. So, that result that we got is matching. Now, let us look at another situation where you have the capacitor C excited by an EMF V of t. So, if this is the current I of t, then this, as I said in the previous lecture, do not mark this as, let me call this V c of t. Do not mark the arrowhead on both sides, because this is positive negative, the current is going like this. With the current going like this, this should be the drop. If we are going to write V c of t is the same as V of t. Now, let us arrive at what is the precise way of writing this, because there is usually a misconception in how this has to be expressed. For instance, we will start from, if let us look at this. This is the polarity of the charge q of t on a capacitor CFT. If that is the case, then the charge on the capacitor, the voltage of the capacitor V CFT will also have the same polarity. In this context, we know that Q of t is equal to C V CFT. And therefore, if I were to call this current as I of t, then I of t is the differential of the charge dQt by dt, which is C dVCt by dt. All right. Now, with this, the usual mistake that we find in several places, several students are misled like this. The usual mistake is, now if I want to get Vc of t, they write Vc of t equal to 1 by C integral I of t dt. Now, there are two problems in this expression. The first thing is, this is a function of time, whereas on the right hand side you have an indefinite integral, which means you do not have the limits for these two. If you write an indefinite integral like this, you are going to get a constant of integration. That is not given here. Therefore, this is not the correct way of writing it. Besides, let us look at what this means. There are people who are going to write this as 0 to t. Now, even this form of writing is wrong. Let us see what this means physically. Let us look at this integral. What it says is, if you have an I of t like this, let us say this is I of t, this is 0. What you are telling here, for instance, is you are integrating between 0 and t, which means this is 0, this is t. Now, this is meaningless because t is the variable here. When you write dt here, it means that t is the variable of integration, and you are also telling that t is the limit of integration. That is totally meaningless. The same variable cannot be the variable of integration, the same t cannot be the variable of integration, and at the same time the limit of integration. For instance, you cannot say t goes from 0 to t. It is absurd to make such a statement. All right. Therefore, since we want something like this, we will call this as 0. We want this area, which is what we are talking of there. Therefore, it does not matter if I change this variable. All right. I will say this is now I of tau, which is another dummy variable, and this area is what I wanted. Therefore, I will say the left hand side has to be the function of time. Therefore, I will put this t here, and I am going to make this 1 over c integral tau equal to 0 to t v I c of tau d tau. All right. This is how it must be written. Even though here you do not have the tau coming into picture, when you have to write V c of t as an integral using integral of the current, you must write it this way. You must never write this as I c of t dt, and here you can't have the limit of integration as t and the variable also to be t. No, that is meaningless. So, please use it like this, and the previous form which I told you was wrong. Now, the question is whether I should write it 0 to t or minus infinity to t. In general, you can write it as minus infinity to t, and if you do that, then you are going to get this form V c of t equal to 1 over c integral minus infinity to t I of tau. I am not writing t here, I c of, now this is just I, all right, because I called it I here, I of t. So, I call it I of tau d tau. If I write it like this, I can write it as 1 over c integral, please observe this is tau going from minus infinity to t. I can split the integral tau going from minus infinity to 0 plus 1 over c integral tau going from 0 to infinity. Okay. Then this becomes I of tau d tau, this also is I of tau d tau. I split this integral tau going from minus infinity to t to tau going from minus infinity to 0 and then from 0 to infinity. Now, if you will see this object, what this says is you are passing a current through a capacitor since how long I don't know. I am going to call it as if it is coming from minus infinity, and this current is passed through into the capacitor up to time t, and when you integrate the current you will get charge. So this part which I have marked here is the charge on the capacitor at t equal to 0. Therefore, I can now write this as, please observe, I wrote it as q of t, therefore this becomes q of 0, right. And in this expression, when I wrote this as tau going from 0 to t, it means that if I am going to get only this, it means that the initial charge on the capacitor, which is q0, is 0, which means initially the capacitor is uncharged. You have seen in the discussion on initial conditions that the charge on the capacitor cannot change instantaneously, which means the charge on the capacitor, if you take it as q0 minus, that will be the same as qc 0 minus will be the same as qc 0 plus. The charge on the capacitor cannot be discontinuous, it cannot have a jump at any time, it must be continuous with respect to time. Therefore, it does not matter whether I write this as 0 minus or 0 plus. And if that charge, initial charge on the capacitor itself is 0, you will get this going to 0, therefore, you will get this value. So, we must be careful to write either this form or tau equal to minus infinity to t, depending on whether the capacitor is charged or uncharged. Now, we have another problem. So, let us come back to this. Let us take this expression now. So, V c equal to this, which is 1 over c integral tau. I am not going to write t, please bear that in mind. It is a dummy variable. You can write this as x, z, anything you want except t, because you have t on this side. Tau equal to 0 to t I of tau d tau. Now, if I have to take the Laplace transform of this, you will recognize that I have the Laplace transform of this, which is the Laplace transform of 1 over c into integral of a function. In the case of an inductor, we saw that we were required to take the Laplace transform of the differential of the current, whereas now we are required to take the Laplace transform of the integral of a current. Okay. So, we require another formula for that. Now, the question is, I can actually go and compute Laplace transform of integral of tau equal to 0 to infinity, or even minus infinity to t e to the power of I of t f of t f of tau d tau. I can compute this directly. All right. If I were to compute this directly, this becomes, first I take the Laplace transform. So, let me, this itself is the function, please observe, this itself is the function for which I am taking the Laplace transform. Okay. So, that I am going to write here. So, what is that? That is integral tau equal to minus infinity to t f of tau d tau. I have got this. Now, I must take the Laplace transform of this. So, I have e to the minus st, this is a function of time, therefore, I am writing e to the minus st here, dt between 0 and infinity. I can actually go and compute this integral of an integral and get the formula for this, but then just for the sake of a change, I am going to do it differently. Normally, you may not find this in your books, but then there is an easier way of arriving at the Laplace transform of an integral. For that, let us go back to what we already know. Given L of f of t equal to f of s, which means you have a Laplace transformable function f of t, the Laplace transform of which is f of s. We have L of f dash of t equal to s times f of s minus f 0. All right, this is the formula which we already know. Now, just as I said, for this to be valid, f of t must be Laplace transformable. Technically, before I can write this, I must also say that f dash of t must be Laplace transformable, all right, which means this must also be, as we saw in the beginning of this lecture, regular, and it must be of exponential order, all right. But then fortunately for us, most of the functions that we are going to see are going to be having derivatives which are Laplace transformable. So, we need not check in the problems that we solve whether the function is Laplace transformable or not, except in the case of some funny cases where you have tan x tan omega t, as we saw, all right. But when we do not encounter such signals in real life, therefore, it is fine. Now, using this itself, what I want to get is, what is the Laplace transform of the integral? What have I here? The Laplace transform of a function. With that, I am going to get the Laplace transform of the differential of the function, all right. Now, with this, can I use this to get Laplace transform of integral of f of tau d tau, integral of a function? Can I use this? That is the question, all right. To do that, let me introduce a new variable. Let g of t, I am introducing a new function, be d by dt of f of t, which is the same as f dash of t, all right. If I have this, then please observe, d by the differential of f of t is g of t. Therefore, what is f of t itself? F of t must be the integral of g of t, all right. I will repeat, I am defining g of t as the differential of f of t. Therefore, it says that f of t must be the integral of g of t. That is what I am going to. Then f of t is integral of tau equal to minus infinity to t g of t, sorry, g of tau d tau. So, this is what we have. This can be from minus infinity to t, or if you want, this can be from 0 to t. It does not matter. It depends on whether the initial value that we took there in the case of the capacitor, as you saw, is either 0 or non-zero. We can take it like this, and still there is no loss of generality. We can still arrive at the result that we want. Okay. Now, let us proceed. If this is the case, then what is g of s? Look, what we are doing here is f of t is the integral of this. Now, g of t is this. So, let me take what is g of s. G of s is Laplace transform of f dash of t. Agreed? That is the Laplace transform. What is this now? That is s of f of s minus f 0. All right. This is g of s. Now, what is it that I want? I want the Laplace transform of this. Please understand. I want the Laplace transform of the integral. The Laplace transform of the integral of this, let me use this part of the board. We want Laplace transform of integral tau equal to 0 to t g of tau d tau. We want the Laplace transform of this. That is the same as Laplace transform of f of t by our definition. And the Laplace transform of f of t is f of s. Now, when do we want the Laplace transform of this? Let us modify this statement. Given Laplace transform of g of t equal to g of s, we want that Laplace transform, all right, which means that is, let us take, we want Laplace transform of this integral of tau equal to 0 to t g of tau d tau in terms of g of s. All right. So, let us restate the problem. We want the Laplace transform of this in terms of g of s or something related to g of t. Now, what is this Laplace transform? That is, let us say the Laplace transform of this integral is f of s. That is, we want f of s in terms of g of s. So, that is what we want. Now, let us see what we have got here. I have g of s on this side, I have s f of s minus f naught here. Okay. Let me come back to this. Let me call this equation as star. From star, I want f of s in terms of g of s, which means I want f of s, for instance, on the left hand side, everything else on the right hand side. So, let me simplify this. From star, I will take this to the left hand side, I will take the others to the right hand side. From star, s times f of s equal to if I bring this to this side, I get g of s plus f0. All right. Let us understand this. I am taking this s of f of s is g of s plus f0. What I want is s of f of. So, let me do this. I will do the simplification here itself, divided by s. All right. Now, let me look at what is f of 0. What is f of t? F of t is this. Where is t sitting? T is here, t is sitting there. So, if you had taken this integral as going from minus infinity, then you can say that this is the same as g of s by s plus you have 1 over s. Then if t f of t is when this t goes to 0 and this is f of t, as t goes to 0 I must put the upper limit of the integral as 0, that is tau equal to minus infinity to 0 g of tau d tau. Okay. So, this is the final formula that we have without actually going by the other method. So, let me write again. The final formula is, now I got the Laplace transform of the integral of g of s. Now, instead of g of s, I could have had any other function. So, the Laplace transform of integral of g of tau, integral of g of t, which is now g of tau d tau, tau equal to minus infinity to t, is g of s by s plus 1 over s integral tau equal to minus infinity to 0 g of tau d tau. All right. So, compare this with Laplace transform of is d by dt. Instead of f of t, I am going to write g of t is s g of s minus g0. So, this is the formula for the Laplace transform of the derivative of a function. This is the formula for the Laplace transform of integral of a function. I could have written it as g or f, does not matter, because that is not the point. You can get any function there. Let me take for our example the function to be current. If I take the function to be current, then I will get here I, then this becomes, instead of g of s, this becomes I of s, the Laplace transform of the current, into this I of tau d tau, and here if I have I of t, then this becomes s times I of s minus I0. all right. Now, we saw that in this context it is applicable to the case where we saw L di by dt, which means that was the current through the inductor. Now, here I am not in particular writing it as I0 minus or I0 plus, because in the case of the current through the inductor, you know that I0 minus equal to I0 plus in L. It is for any time, in particular for 0. Therefore, I am not making a distinction here between 0 minus and 0 plus. If that distinction has to be made, then you can take it appropriately. Now, in the case of the capacitor, what is this now? We saw earlier that in the case of the capacitor, this is the current passed through the capacitor from I don't know how long back, I will call it minus infinity to the starting of the clock, which is at 0. Therefore, this becomes the charge on the capacitor. So, this, if you were to rewrite this, this becomes the current through the capacitor I of s by s plus 1 over s QC 0, because this is the charge on the capacitor at time 0. I called it as QC 0 or Q 0, does not matter. Now, if the charge on the capacitor at time t is 0, which means if you have an initially uncharged capacitor, this will go to 0. If you have an inductor in which the initial current is 0, this will go to 0. Otherwise, these two terms will appear. So, you must be careful in applying these two. All right. So, let us take, for instance, one very simple case of a circuit and analyze and then close our discussion, because that is where we are going to see an application of these principles of Laplace transform. Let us take a simple RL circuit. Let us call this I of t, and let this be a battery, a constant voltage V. Now, what is the problem statement in this case? The problem statement is find switch K closed at t equal to 0, and before the switch was closed, the circuit was in equilibrium before t equal to 0, which means if it was in equilibrium, there was no current through the inductor. So, that is straightforward. From the exercises through the initial conditions, you know that. Okay. Now, let us put the initial conditions and then proceed. Now, you know that this is the current through this current is the same as this current. So, I am going to write it as I of t instead of here, it is the same. Now, please observe, I am not going to mark this V of t or VL of t with arrowheads on both sides. If I do that, I do not even know how to write the equations. Therefore, I am going to write this with arrowhead only on one side. The current is flowing like this, the drop across this is taken opposite to the current, direction of the current, the drop across L is also taken as direction opposite to the current. So, from initial conditions, I will call this ICs, from the initial conditions we know I of 0 minus is the same as I of 0 plus. Why? Because it is the current through the inductor. It happens to be the current through the resistor, but what is important for us is to consider that it is the current through the inductor. So, I of 0 minus is the same as I of 0 plus, which is 0 ampere. Now, please be cautious, just because you get a value I of 0 minus equal to I of 0 plus, do not write it as 0. 0 there does not have any meaning. For instance, if you have the drop across, if you have the, in some other case, if you have this Vc of 0 minus is Vc of 0 plus, if you write this as 0, this is not correct, because these two, if you look at only the right hand side of these two, they appear as this something equal to 0, something equal to 0, but please observe they are different physical quantities, and we are here as engineers, we must not do this mistake. In this case, I must call it as 0 ampere, even though it is 0, I must call it as 0 ampere, and the other one I must call it as 0 volt. Just because you get 0, for instance, if you get dit by dt at 0 plus equal to 0, if you write it like this, it is wrong. You must write it as 0 ampere per second, because it is a physical quantity and it is not just a number 0. There is a difference between the two. So, just because you get 0, do not forget to write the units. Caution to the students. So, here you are going to write this as the initial current is 0 ampere. It can be milliampere or whatever, but then this is not going to be millivolt or volt. So, therefore, I need to write the units. People might ask, how does it matter whether it is ampere or milliampere? Well, then it does not matter. However, this 0 cannot be the same as the 0 that you are going to write for the voltage, where it must be the dimension, where it must have something related to do with volt. All right. Now, this is what we have. Now, let us write KVL for this. What is the circuit for t greater than or equal to 0? Let us write the circuit for t greater than or equal. At t equal to 0, this switch is closed. Therefore, this is what you are going to have. You have your L, you have your R, this is VR of t. Please observe the direction of the arrow. I have arrowhead only on one side. This is V, and the current here is I of t. So, this is the circuit for t greater than or equal to 0. Now, let me write our KVL. What is KVL now? V must be equal to VR of t plus VL of t. Okay. And we know, since the current through both of them is I of t, we know how to write this. That is the same as R I of t plus L dit by dt. All right. Let me call this equation 1 for the present. Now, this must be taken with I0 minus equal to I0 plus equal to 0, not 0, 0 ampere. What you have done till now is to take the differential equation and solve, whereas now what we are going to do is we are going to transform 1 using Laplace transform. What do you get is, this is constant and it is starting only at t is equal to 0, which means if I take this constant, and after, which means you are looking at this voltage like this t, and this is V. It is a step of value V. So, the left hand side becomes V by S equal to Laplace transform of this is R I of S plus, what is the Laplace transform of L into Laplace transform of di by dt. So, it is S I of S minus I0. Now, we know that I0 is 0 because of this. So, we are going to write this as R plus SL into I of S, which implies I of S equal to V divided by S into SL plus R. So, now the problem was to find I of t for t greater than or equal to 0. Now, just one word, the way to do that is to get what is called as the inverse Laplace transform. If you take the inverse Laplace transform of this, we indicate it by this, the Laplace inverse of I of S equal to I of t. If you take the Laplace transform of I of t, you get I of S. If you take the inverse Laplace transform of I of S, you get I of t. And then you will see in the next lecture or the subsequent lectures, when you have problems like this, using this you can directly get the Laplace transform of this as I of t is V into 1 minus e to the power of minus RT by L. This is for t greater than or equal to 0. So, this is the expression that you will get for V by R this is the expression that you will get for I of t by directly using the partial fractions method and splitting this, and if you do that, this is the expression that you will get, and it is straightforward. So, that is the power of Laplace transform, which you will be seeing in the subsequent lectures. Thank you very much.